Probably to like one page.
I don't know, but you could also, I mean, it depends like what type of laptop you do, but then you can put it in OneNote and like draw on top of it.
Yeah, but then it's like I tried trying to switch to like OneNote and like drawing on my computer. I would need a good stylus. My computer is touchscreen, but it's just like
Yeah.
I can't like do it with my like fingers. So
Oh yeah, no, don't use your fingers, you can't. I was watching Ben at like the start of class, like yesterday, and you know how he told us that story about how he holds his pens weird? He was doing that, and I was just like, I don't know, I was just like, how do you do, I was trying to picture like how you would do that, and he just like, oh, no, but he was like writing something, and I was like disgusted. Repulsed to my very core. March 8th. When's your birthday?
it's around.
You're one of those people?
Okay, morning everyone.
You have to like go find your Facebook and like look.
I don't have that.
Let's get
Oh, I do have
started.
that. Okay. Now I can change my birthday.
Okay, quick reminder, if any of you were from the second midterm, in the situation that you attempted to use energy conservation for that problem, you have your script and haven't yet handed it in, please do so today. All right, so we'll talk about gravitation for the morning. Continuing talking about Newtonian gravitation for the first maybe half hour, see how quickly we can get through that, and then turn our attention to other ways of describing gravitation, in particular general relativity, though I may mention a couple of other things along the way. So first thing I want to talk about is returning to the idea of gravitational potential energy. Remember, we've been using this pretty much from the start of the semester in the case of near-Earth surface gravitation. And of course, the expression that we defined there, or arrived at with our usual definition of change in potential energy, of being the negative of the work done by a conservative force, is that the gravitational potential energy near the Earth's surface is just m times g, local acceleration due to gravity, times whatever height our object is at. And in particular, it's the difference between heights that gives us differences in potential energies. So we're going to go back and do the same calculation quickly, but now with our more general Newtonian gravitational force law, which is this one, and see what we come out with in this case. So let's jump in straight away, and let me remind you that, as always, our definition of potential energy, in this case, again, gravitational, is the negative of the work done by a conservative force, so the gravitation satisfies that requirement. So I'm going to write this as integral of F dot dr, as usual. So something that looks like this. And maybe we're moving from, let's say, a force between two objects, let's call it A and B, and we're having them start off at an initial separation between their centers of R1 and a final separation between their centers, which is R2, okay? So our standard definition of the gravitational potential energy change. So, okay, we know this. Let's go ahead and plug this in. And so I'm going to write this now as the work done by gravity integral from R1 to R2. And now let me just make sure you understand the sign associated with this. So just take a look at what I've done going from here to here. So obviously my standard expression for the large-scale Newtonian force MA, MB now, rather than M1, M2, because I'm talking about objects A and B, separation R squared. So the thing I really want to draw your attention to is just the minus sign, and how I might be folding this into my calculation. R, of course, we are counting as the distance between the centers of these two objects. And so as R increases, the objects are getting further apart, but the force, of course, is against that sort of direction of increasing R. So it's an attractive force. And so the minus sign really is an indication of that. And so in terms of increasing R, when R is increasing, my force is in the opposite direction. So I'm throwing in a minus sign here to reflect that. Okay? So now we've got this as our definition of the work done by gravity. Simple enough integration. So this now becomes plus G and A and B over R, evaluated between my separation limits. And of course this just now becomes G and A and B over R2 minus G and A and B over R1. So that's the work done by gravity. But of course, as always now, as I immediately carry this over into the change in gravitational potential energy, I need to flip the sign. So in this case now, delta Q is the negative of this. We make that a true subscript. And so I'm actually just going to flip the order here and write this as G and A and B over R1 minus G and A and B over R2. So now we've got an expression that tells us the change in gravitational potential energy as I change the separation of these two objects, and it's simply given by this. So pretty straightforward. All right. Fine. Let's talk about what we did to some extent when we talked about near-Earth gravitational potential energy. So remember, we're pretty much always talking about the change in potential energy here. And since it's the changes that concern us, we, in most cases, have complete freedom to sort of choose where we set the 0 point of that energy scale. So think back to what we were doing with near-Earth gravitation. We often, for convenience, if I was interested in saying something about the change in gravitational potential energy as I pick up this piece of chalk and throw it upwards, we'd often, for convenience, choose this height as being the 0 point of our gravitational potential energy. And again, we're always interested in differences, so we have the freedom to move that 0 point wherever we like. So in principle, the same is true here. And the question is there a more natural place that's actually sort of defined by something physical here that would be a good point for us to define the 0 point of this? So the question is, what's a sensible 0 point for U gravitational? So, just think about that for a moment. Given now that we have got a more general force law, is there a sort of physically reasonable point that you might actually choose to set the 0 point of your gravitational potential energy scale in this case? Okay, let's go RL.
R being infinitely far away.
Okay, R being infinitely far away. Motivation for it?
You said one of the terms for U will cancel out to 0.
Yeah. And more specifically, of course, if you look up back at the force law, when I've got infinite separation, the force is actually 0. So asymptotically, this goes to 0 and the separation becomes infinite. So in this case, there is actually a kind of physically sensible place to define the 0 point of gravitational potential energy. So I'm simply going to write this as since f of infinity goes to 0, it's somewhat natural to set the corresponding gravitational potential energy to be 0 as well. And we'll typically do that, okay? Now remember, it's kind of still a choice, but in this case it's a little bit more strong motivation for doing so. So this is at R equals infinity, and this is at R equals infinity as well. So that's typically what we're going to use. And in that case, what I can say is I can go from talking about a relative or change in gravitational potential energy to what I might call a sort of absolute. It's not really absolute, it's simply in the sense that we've chosen this as our 0 point. So an absolute gravitational potential energy, which I'm simply going to write as the following. As that, okay? So what does this look like? Maybe I'll highlight this as kind of sufficiently common that we'll use it a lot. What does this look like? So if I simply plot now gravitational potential energy under this assumption or under this definition as a function of separation. Again, by this convention, an infinitely large separation between our two objects, the gravitational potential energy is 0, and as I bring them together, this thing has a 1 over r dependence, and of course it's negative, right? So let me just let that sink in for a moment and make sure you're okay with this. So remember, again, potential energy, we always have the freedom to choose our 0 point wherever we like. We've happened, in this case, for physical reasons, to choose the 0 point of infinite separation. This gives us this definition of the relative potential energy as a function of that separation. And again, with this choice, it's always negative. So don't be too perturbed by this, okay? Again, it's changes in energy that ultimately are typically what we're concerned about, but don't be perturbed by the definition of this as being negative for all separations, at least unless we get to infinite separation when it's 0. Everyone okay with that? Yeah?
How do you first term cancel out when it becomes 0?
So if I'm choosing one of these to be infinite, then of course I'm dividing by infinity, so that term is going to drop out. And just remember which way round I've got this. I can't remember which ones are 1 or 2 here, but for infinite separation, that term is going to go to 0. Questions about that sort of definition of gravitational potential energy? Okay, good. So let's use that right away for some things. First thing I'm going to talk about is the idea of an escape velocity. We mentioned this earlier in the semester. But now we're at a point where we can actually define it a little bit more crisply and maybe even do something useful with it. So, what do you recall from how we introduced the idea of escape velocity? When you think of that, what do you think of when you hear the phrase escape velocity? So some object, I think I have a small ball here, throw it upwards. Obviously our experience is that eventually it turns around and comes back down. What is escape velocity? What is it talking about? Yeah?
The velocity required for an object to escape the gravitational.
Okay, right. So if of course, the harder I throw this, the higher up it goes. So the question is, can I throw it hard enough that it essentially escapes the gravitational field of, in our case, the Earth? Well, does it ever fully escape the gravitational influence of the Earth? Okay, not really, right? Because gravitation has infinite range. But is there a way that, given what we've just talked about here, that we might kind of define an effective escape from the Earth's gravitational pull? And how might I define that? Yeah.
Oh, is it with R also?
Okay, so it's very far away, it's infinitely far away, so I can certainly imagine R going to infinity. But beyond that, how might I precisely define what it means that I've actually escaped? How might I define that in a way that I can make it useful? Yeah. In the beginning.
Is it when the force of you throwing the thing is greater than the force of gravity?
Okay, I mean, in a sense, yes, but what does that mean as I get infinitely far away? A little louder. Nice way to start thinking about it, when the kinetic energy exceeds the gravitational potential energy. So certainly, if that were true, you could imagine that it's always got enough kinetic energy to overcome the attractive force of gravity. So what is it that defines exactly that boundary, if you will, that threshold? Yeah?
The centripetal acceleration that we did. We did what?
I'm, let's say, shooting this thing vertically upwards, so it's on a radial line away from the Earth. So there's presumably no sort of circular component to the motion. Okay, good. So the boundary condition would be, in fact, when the initial kinetic energy equals that gravitational potential energy that it has. So think about that. I give this thing just enough initial kinetic energy that as I throw it upwards, as we know, it's losing kinetic energy as it goes upwards. What's happening is that kinetic energy is being transformed over into increased gravitational potential energy. But if I can define that threshold point essentially in the way that as it gets infinitely far away, slowing down and slowing down and slowing down, and it asymptotically approaches zero velocity at infinite separation. That's actually the boundary condition, and that's how we're going to define escape velocity. So we're going to use that as our definition effectively. So this is to say that the velocity at r going to infinity approaches zero. And so we're actually going to use that equality, that it actually equals zero at infinite separation, to define this. So yes, in terms of energy, which is the easiest way to think about this, in terms of energy conservation, let's see if we can figure out what the criterion is. So I'm going to apply energy conservation in my initial configuration and compare it to in my final configuration. So let's look on this side to begin with. I'm firing my object vertically upwards, and I'm firing it from, let's say, the Earth's surface. So let's see what I can say about the terms here. So I'm starting this off with some initial velocity, VI, and so the kinetic energy associated with that is VI half m VI squared. And now I'm launching this from the Earth's surface. In terms of our new definition of gravitational potential energy, what do I need to put here for the gravitational potential energy at the launch? Launch. So remember what we've just taken as our 0 point for gravitational potential energy, now that we're talking about large-scale gravitation. So I think the fact that you responded 0, you're kind of wanting to go back and think about near-Earth gravitation, where we've got a constant force and a constant, yeah.
Using the radius of the Earth.
Right. So in fact here, what I need is minus, let me put this in terms of notation that's maybe a bit more specific to this case. This is going to be the mass of my Earth in this case, the mass of my object, and then I need the radius of the Earth as being the r value that I'm starting off with. Okay? So I've got this as my sort of initial balance sheet, if you will. And I need to add these two things together. That's the total energy with our definition of 0 point of gravitational potential energy, as we've just talked about. That's the left-hand side. I need to balance this now with the total energy once it reaches this criterion that it's infinitely far away and it's just asymptotically coming to a rest. So what would you say I need to write for the u and k terms at that final point when it's infinitely far away? What do we need to put for the two terms there? 0 for both. That'll work. By definition, infinite separation, that's our 0 point now. And again, sort of by definition, when we're talking about escape velocity, this is when it asymptotically goes to 0. So this, in fact, is my escape velocity condition. And I can simply go ahead and figure out what this is. So I need to write this as, let's see, VI squared equals G and E M R RE, and then I need to multiply this by 2. I need to divide by little n. I get this cancellation, and if I've done this correctly, I find that this is the square root of 2g mass of the Earth divided by the radius of the Earth. Okay? So I'll just make sure you're okay with that derivation. Look all right? So this now defines for us the velocity needed to escape from any massive object, mass m, radius e, this is the launch point. This gives us the velocity that I must have in order to satisfy this condition, and so in a sense to escape the gravitational force of the Earth. It's not really escaping as we talked about a few moments ago, but it's now defined by this condition that I just go to zero speed at infinite separation. Good. Okay, so this is a kind of useful energy conservation analysis that allows us to say something about escape velocity. As always, I try and sort of touch base with relevant real-life examples. Anyone know what this turns out to be for the Earth? Yeah. 11 meters per second. Okay, don't laugh too hard. We already had other interesting, say, powers of 10 discrepancy earlier in the week. Go ahead, you corrected yourself. Okay, so it indeed is around 11 kilometers per second. I think formally it's 11.2. So it's approximately 11 kilometers per second to arrive at this condition for launching something from the Earth. Okay, good. Any questions on that? I'm going to, if not, move on and turn our attention to the question of orbits, things around massive central objects. Okay, takeaways from this: energy conservation and the slightly, maybe uneasy aspect of saying a 0 point of large-scale gravitational potential energy at infinite separation. So what that, of course, gives us is at any point in this scenario, we have positive kinetic energy, negative potential energy, and then the trade-off between the two. Okay, now let's turn our attention to orbits. And I'm always a little bit unsure about how much to do with this in a course like this, but I'm basically going to just introduce and to some extent motivate so-called Kepler's laws. There are 3 of these, and they have to do with sort of generic properties of orbits or maybe slightly more precisely of orbiting objects around a central mass. So, of course, prime example of this would be either a moon around our Earth, or maybe on a slightly larger scale, planets around our sun in the solar system. And so Kepler's laws have a pretty long history at this point. They were first really determined in the early 1600s, so 400 years ago. I'm going to sort of describe them relatively quickly, and not surprisingly, of course, they are results that are entirely consistent with Newtonian gravitation. So they are basically just sort of corollaries of Newtonian gravitation. Okay, so here we go. First one, so-called law of orbits. I'm going to ask some questions, but I think I'm just going to move ahead fairly quickly here. So, based on observations early on in our own solar system, but later on much larger scales, it turns out when we're talking about objects and their gravitational attraction to each other, we always find that objects moving around what I've called a central mass, and we're about to qualify that in some way, we always find that they're moving in elliptical orbits, okay? So, let me quickly tell you what I mean by this. So, all, let me call them generically planets, move in elliptical orbits around, and I'm still calling this central, but of course it's not actually at the center, because in general these are ellipses rather than circles. All planets move in elliptical orbits around the central mass, with that mass being at one focus of the ellipse. Okay, I apologize, that's not the cleanest way to write this, but let me just quickly draw this out so we can see what we're talking about. Here's the central mass, big N, is an orbiting object, a planet in my language. And it is moving around this central mass in an elliptical path. And what I'm going to do, this will relate to the second law, Kepler's law, in just a moment, but I'm going to draw a line that connects the central mass to the orbiting object, so distance r in this case. It is defined at any particular instant to be at an angle theta with respect to the major axis. And then a couple of things from geometry, which you may or may not remember. When we've got an ellipse like this, if I look at the long side of the ellipse, and then look at half of the length along the long aspect of the ellipse, this is what's called the semi-major axis, or semi-major sort of length here. And then the other thing I want to add on this, and I'm getting a little bit short of space here, let me draw that up there, and then off on the side, so hopefully you can still read it. I'm going to define this distance. So that distance is E times the semi-major axis of the ellipse. And this thing here is what's called the eccentricity. Okay, so a lot going on in a short space of time here, but probably many of you have seen this before. So quick summary. First off, in general, we're seeing that these planets are moving in elliptical orbits. The central mass is at one of the two focuses of the ellipse. And then we can parameterize the shape of the ellipse in terms of its semi-major axis and the eccentricity. Okay, quick bit of general knowledge. In our own solar system, any sort of rough idea of what sort of eccentricities are kind of observed in our own solar system, or in fact maybe what the eccentricity of the Earth's orbit is? Yeah.
Just slightly under. They're almost all circular, right?
Okay.
I don't remember. Is it 0 or 1 circular? So it's like, I think the Earth is like 0.998 or something like that. Sorry, from 0 to 1, like the.
So the opposite, the inverse of that.
Is it the inverse of that? Is it 0.0017? Or 0.017 is the Earth?
It turns out it is. So the eccentricity for the Earth is about 0.017. Okay, so it's a small number. Thanks for the assist there. It's a small number, which indeed tells us that for the Earth's orbit, it's close to circular. It's not perfectly circular, but it's close. If it were a much larger eccentricity, how would that impact our life here on Earth? Yeah.
Probably have seasons having to do with closer axis to
You have very dramatic seasons, right? Because at some point you'd be much closer to the central mass, which is the sun in our case, than at others. So the fact that we're actually on a close to circular orbit turns out to be very important. And in fact, whenever people are worrying about, planets in other solar systems, perhaps, the eccentricity is an important issue, because if you want life in sort of stable conditions, you better have relatively small eccentricities. Otherwise, you're dealing with massively different environments, if you will, at different times of the orbit. So yeah, the Earth is close to circular, and that's true, in fact, of all of the planets in our solar system. All right. So that's in fact the first of Kepler's laws, the idea that planets move around in elliptical orbits. Let's talk about the second one, and this tends to be called the law of areas. And it basically says that if I look at the motion of this object orbiting around the center, and in a certain time interval, it moves, in this case, it's